In this screencast, we're going to continue our investigation of looking at the step response for the situation where we have a dominant pair of complex poles. But this time, instead of having real zeros or real poles that are nearby, we're going to have complex zeros that are close to our dominant set of poles. Okay, so let me draw what's happening in terms of a pole zero diagram. So here's the j omega axis. Here is the real axis, sigma. Okay, and this is similar to the study that was done in the book. The book takes a pair of poles that are very lightly damped. Okay, so zeta is equal to 0.1. So we have poles here and here that are relatively close to the j omega axis. Okay, and so we're doing that so that we can see the ringing effect. You know, with the zeta equal 0.1, this is underdamped, and we should see a response that looks like this with lots of ringing. Okay, and indeed we'll see that that's true. Okay, so let me get rid of that. And now what we want to do is model what happens when we put a pair of zeros. Okay, so I'm going to do it like this. A pair of zeros relatively nearby this complex set of poles. Okay, so hang on just a second. So let me say I had that here and here, and so what I'm going to be looking at is what happens when I take this complex pair and put them near. This should be lined up a little more. Okay, so near the poles where they're almost canceling. All right, and we'll see that's actually pretty good when that happens. And as we move this away, what happens to the step response? Okay, so we're going to use different values of alpha. Okay, and this time alpha is going to literally be the real part of the root. Okay, I'll go over the model here in a second. As alpha gets bigger and bigger and bigger, it's moving more and more to the left. Okay, and that pair of complex zeros is moving further to the left. All right, the catch is, with this model, we have a system that can't be physically realized. We need a proper rational polynomial. So we need the order of the top to be less than the order of the bottom. Okay, so we can make that happen by putting another real a real pole relatively far away. Okay, so let's say, you know, this is at 0.1. Let's say that we have a pole out here sitting at, say, -4. Okay, so that's what our model is going to look like. All right, so we could look at s plus alpha squared plus beta squared. That gives us a complex set of zeros. And on the bottom, we have our usual s squared plus 2 zeta omega n s. Remember, we're going to use omega n equal 1. Okay. And then I'm just going to go ahead and put s plus 4 here. And then in the code that I write, I'm going to put a gain constant c so that the overall final value of the response heads to 1 no matter what value of alpha that we use. Okay? And so we're going to use normalized frequency again, and so the way that works is we're going to let omega n equal 1, and for comparison purposes we want the zeros to sort of fall along the same imaginary part as the poles do, and so essentially what we're saying here is beta is also equal to 1. And so we're going to take a look at various values of alpha. So we're going to have alpha really close. Actually, we're going to take alpha equal to 0.1. What happens there is the poles and the zeros cancel. Okay. Of course, in real life, it's hard to get them to exactly cancel, but we're going to see that's a good effect when those do cancel. All right. Then we're going to mark this out 0.2, 3, make them more and more to the left and see what happens as the complex conjugate pair moves to the left. Okay, so that's what we're going to do in MATLAB. So I'm going to break for. Okay, here's the screencast where we're looking at the effect of complex zeros on a second order response where we have complex dominant poles. Okay, so as we've done with all these, we first set up an object. This is the transfer function object where we set the variable s to denote that. And then we're going to be looking at various values of alpha. And as I said previously in the video, as you let alpha equal 0.1, at alpha equal 0.1, the poles, complex poles and the complex zeros cancel. So we see that effect. And then at alpha equal 0.2, the poles and the zeros are only 0.1 apart. And then we're moving them further and further apart as we increase alpha through various values. Okay, so by the time we get to alpha equal 10, the complex zeros are pretty far from the complex poles. Again, we're going to use a particular zeta value. You can change this, but that's something that we've set up. All right. This is modeling our ideal response. Remember I told you we need to add a pole at -4 so that once we add these complex zeros in our study, we still have a proper polynomial. So let's go ahead and use this as a comparison. So this 4 out front is to get the overall gain to be 1, so that the final value is 1. Okay, I'm sorry, the DC gain should be 1, which gives you the final value being 1. Okay, so we'll calculate that and call it the what we're going to call the ideal response. All right. Then I mentioned in the video also that I needed a constant c so that the overall transfer function has a gain of 1 for all values of alpha. So this is the value of c that makes that happen. And then you see in the numerator here, I have a set of complex poles with the real part being alpha and the imaginary part being 1. Okay, so from this we can take a look at what happens. All right, so I'm going to run this now. Okay, and what should pop? Oh shoot, I forgot to clear the figure, so we'll have to let that run for a second. This is going to make a jumbled mess. Okay. Sorry about that. Okay, so now we're ready to do this. Here is what we're calling the ideal response. So you see there's overshoot. The first case at alpha equal 0.1, the poles and the zeros actually canceled. Okay, let's see if I can zoom in and get that case. Now let's run it again and pause it. Okay, this is ideal. This first one, notice we still get a pretty rapid response, but the pole and zero canceled and we got sort of a nice looking response there. Okay, as you move the complex conjugate zeros away from the complex conjugate poles, you start to notice that I'm going in the direction of this arrow, so you track the colors from the legend. But I'm speeding up the response, but I'm getting this weird kind of rippling effect in the middle. Those are probably okay for what you'd want in a control system. But as you move further and further away, the advantageous effect of the complex zeros diminishes, and in fact you start to get increased overshoot. The rise time improves, but the overshoot actually increases. And then there's this weird phenomenon that if you keep increasing it, this actually starts to go back down and converges back towards the ideal response. So you see, again, file it away. Nearby zeros and poles are going to affect the step response. So you can't always use those parameters like we did on exam 1 that characterize rise time, overshoot, settling time, those kind of things. All right. So that's the point of this whole video series, is to take a look at that, to try to give you a feel for what's going to happen when you have nearby poles or zeros. All right, so that's going to be in your toolbox for doing designs later on when you start adding controllers that end up placing poles and zeros in various locations.